and network security series. In this video, we'll be speaking about Diffie-Hellman key exchange algorithm. So we'll understand how the algorithm works firstly. We'll look into the exemplar problems. We'll see what are the advantages, disadvantages, what are the key exchange protocols, and the vulnerability to man-in-middle attack and how to overcome that attack. So make sure you stay tuned till the end and you don't miss out any of the videos. Subscribe to my channel. If you have not checked out my CNS playlist, I have tried covering all the important topics of CNS subjects. So do check that out. So let's get started. Firstly, understanding what Diffie-Hellman key exchange is. So we know there's a sender and there'll be a receiver. So whenever the sender and receiver are communicating, one of the main things here is the ciphertext, which needs to be kept confidential, and the attacker should not be able to understand this. And along with that, we have shared secret key also. So if attacker gets to know what is the secret key, he or she will be able to deduce the content on that ongoing transaction, and even in future also he'll be able to deduce content from that key. So in that sense, while sharing the key over a public channel, it becomes very important. And in order to increase the security perspective, we make use of Diffie-Hellman key exchange algorithm. So this algorithm is a cryptographic protocol which is used to secure exchange cryptographic keys over a public channel. So this was first introduced in 1976 by Whitefield Diffie and Martin Hellman. So we derive Diffie-Hellman from these two names of the founders. So the primary or the main purpose was to establish a secret shared key between two parties, which could be subsequently used for the symmetric encryption. So this was just the basic introduction of Diffie-Hellman key exchange. We'll look into the algorithm, we'll understand it very clearly. So algorithm again is very simple, and you can write it very easily also. So the first thing which we have is, we have two communicators here. So first we have is the Alice, the sender, and Bob being the receiver. So the first step is, we have publicly known values here. So we make use of two values here. First one is prime number, which is called as Q. So we are taking a large prime number, okay, and along with that we take alpha. Alpha is called as primitive root of Q. So Q and alpha both should be known by the sender and the receiver. So that's why these two values are known as the publicly known values. So that's what first box depicts. Secondly, we'll be calculating the private key. In order to calculate the private key, we are randomly selecting the private key depicted as XA, and on this side we are depicting it as XB. So this XA or XB, we have to select the private key such that they are less than the random number Q, okay, the large number. So we have selected the private key also. Then we have third step is to calculate the public key. So in order to calculate the public key, we depict public key by YA. YA is equal to alpha of alpha power XA mod Q, and here also YB is equal to alpha power XB mod Q. So after this step, firstly we had the publicly known values, then we calculated the private key, then we calculated the public key. So private key, public key are calculated. My next step is, I'll perform the key exchange. So that is, Alice will send YA to Bob. YA is public key of A to Bob, and Bob will send public key of his public key to Alice. So here the main twist comes is when Alice and Bob are exchanging their public keys to each other, okay, and in order to calculate the public key, we should know what the private key are, right? So that's what we have seen here, alpha power XB and alpha power XA. So these two are privately known. These two are privately selected by the users or the people or the person who has in charge over that particular operation, right? So here Alice, in order to generate Alice public key, we should know what is Alice private key. So only after knowing Alice's private key, we'll be able to generate Alice public key, and it holds the same for Bob also, right? So once the keys are exchanged, so Alice will receive Bob's public key YB in plain text, and Bob will receive Alice public key YA in plain text. So now after receiving the private keys, they'll perform the shared secret calculation, shared secret key calculation. So in Alice side, in order to get the secret key, K is equal to, firstly we'll consider Bob's public key to the power Alice private key mod Q, and on this side again we'll consider Alice public key and Bob private key mod Q. So by making use of these two calculations, we have to get K value as same. So since we know that K is equal to alpha power XA into XB, so mod Q. So both these computations will should result the same value, and thereby we can say that the same secret has been shared along the user and the sender and the receiver. So that's how the algorithm works for Diffie-Hellman key exchange. So here I have written down all the points. So publicly known keys should be taken, then they'll generate private keys, Alice and Bob, and after that key exchange will happen, and then secret key calculations are happening here. And then we know k is equal to alpha power xa into xp mod q. So both the computations will yield the same value. Thereby we can say that same secret has been shared among the sender and receiver. We'll look into what primitive root is. So q is a primitive root. Q is a primary number, and alpha is called as primitive root of q if power of alpha modulo q generates all integers from 1 to q minus 1 in some permutation. So alpha power 1 mod q, alpha square mod q, alpha cube mod q, and alpha q minus 1 mod q should be generated. Suppose if we take example of 7, then primitive root is 3 because powers of 3 mod 7 will generate all integers from 1 to 7. And here if I take q value is 999, then alpha value I have to select something which will get me or yield me all the values between 1 to 998. So that's what primitive root actually means. Next we have examples now. So we'll look into the first example. Consider the public value q, the prime number they have given. We have to calculate alpha and further perform the key exchange. Okay. So in order to calculate alpha value, we have this formula: alpha power I is equal to mod q. So here I is called as discrete logarithmic value, and q such that we have to generate all values till q minus 1 here. So suppose here we have q is equal to 11, right? So we'll take q from 1 to 10. This has to generate the values. Okay. So in order to get that, we'll write down all the powers from 1 to 10 because q value is 11 here. So q minus 1 values will be considered. So 1 to 10 I have written this side, and 1 to 10 I have written this side. These are the d values, discrete logarithmic values, and here I have the power. So I'll calculate alpha I, right? I is here. So alpha 1 power 1 mod q, I'll get 1. 1 power 2 mod q, I'll get 1. That is 1 power 2 mod 10, mod 11, I'll get 1. And 1 power 3 mod 11, I'll get 1. 1 power 4 mod 11, I'll get 1. 1 power 5 mod 11, I'll get 1. 1 power 6 mod 11, I'll get 1. 1 power 7 mod 11, I'll get 1. And so on till 10, I'll get 1 only. Next, 2 power 1 mod 2, I'll get 2. 2 power 2 mod 11, I'll get 4. 2 power 3 mod 11, I'll get 8. 2 power 4 mod 11, I'll get 5. 2 power 6 mod 11, 5 mod 11, I'll get 10, and so on. I'll get all these values. I have to compute all these values for from 1 to 10. But what happens is, once I start from 1, 2, 3, 4, 5, within these values only I'll get the primitive root alpha value. Okay. So if you check here for alpha is equal to 2, we are able to generate all the values from 1 to 10. Right. 1 is here, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all these values are being generated in some computation, in some permutational order. So that's when we can say that alpha value or the primitive root for q is equal to 11 is 2. Right. So for alpha value such that we obtain all values between 1 to 10, alpha is capable to generate all values previous to q. Thus we can take alpha is equal to 2. Once we are done with the first step, that is publicly known values, so we know q is equal to 11 and alpha is equal to 2. Next step is I have to select the private keys. Private keys randomly I have to select such that it has to be less than q. So xa I'll select as 8, 8 is less than 11, yes, and xb I'll select 4 is less than 11, right? I've selected the private keys. After that I'll compute the public keys. In order to compute the public keys, we know the formula. Ya is the public key for a sender. So alpha power xa mod q. So alpha is 2, 2 power 8 mod 11. So when I solve this, I'll get 3. Now yb I'll calculate for b, for the receiver. I'll calculate public key. Yb is equal to alpha power xb. So he's making use of the private key of himself, and mod 11. So 2 power 4 mod 11. I'll get 5 as the answer. So here I have obtained the public keys of a and b both. Now public keys of a and b should be shared with each other. That was our third step. That was our fourth step, right? So the values are shared now. So a has got the public key of b and b has got the public key of a. After that, they'll calculate k value from the sender side. From a side, he'll calculate. So k is equal to, he'll take b's public key first, power his private key mod q. So yb is 5 and yb is 5 and xa is 8. So 5 power 8 mod 11. So when we solve this, we get the value as 4. So k value is equal to 4 here. Next, we'll calculate from the receiver side. From the receiver side means from Bob's side or B side. So here he'll firstly consider the public key of the sender. Public key of sender to the power his private key mod q. So 3 power 4 mod 11 will get the value as 4. We know that for k on sender side and k on receiver side, both should be same. Both should be computational. When we calculate, it has to be same. That's when we can say common secret key is generated. So 4 and 4. Thus, the secret key is k is equal to 4. So that's how we calculate the secret key for the given value. Next example we have q is equal to 23 and alpha is equal to 5. They have given alpha value here. When alpha value is given, it becomes very easy to calculate. So first step, the publicly known values are given. Next we'll calculate private key for sender and receiver. So private key of xa I have taken it as 6. 6 is less than 23. 6 is less than 23, yes. And xb 15 is less than 23, yes. Next I'll calculate the public keys. So public key of sender ya is equal to alpha power xa is the private key of sender mod q is 23. So 5 power 6 mod 23 is 8, and ya value which I'll get is 8. On the receiver side, yb is equal to alpha power its private key mod 11, mod 23. So 5 power 15 mod 23, you get the value as 19. So YB is 19 here. So now that I have known the public key of sender and receiver, I'll exchange the public keys. So YA or the sender will receive the public key of receiver, and receiver will get the public key of sender. After this, we'll calculate the shared secret key. So from sender side, I'll consider the public key of the receiver with the public key of himself and mod q, that is mod 23. So here the values are 19 power 6 mod 23. I get the value as 2. And here on the receiver end, when I write k is equal to ya power xb mod q, that is 8 power 15 mod 23, I get the value as 2. So here 2, the shared secret key is k is equal to 2. So this is again a second example. Now we have the third example. This example is mentioned in textbook. So q value is given, a very large prime integer. So q is equal to 353 and primitive root is alpha is equal to 3. Sender and receiver will select private keys. xa A will select the private key such that it is less than 353, yes, and xb will select 233 which is less than 353, yes. Next we'll compute the public keys. So ya is equal to 3 power 97 mod 353, we get 40, and yb is equal to 3 power 233 mod 353, we get 248. After knowing the public key values, those values will be exchanged, and after that we'll calculate the secret keys here. So when we calculate the secret keys, we get k value as 160. So here the same operations are followed like we have done for the previous two questions. So this was about the examples. Let's quickly look into the advantages. Okay, first advantage is secured communication. So Diffie-Hellman key algorithm will enable both the parties to securely exchange a key without any prior knowledge of each other. So only after calculation of their public keys, they'll share it, and further they'll make use of the public keys and their private keys to generate the shared secret key. Next we have is no key pre-distribution. That is, this algorithm will eliminate the need to share a secret key like in prior. All that is not necessary. Only when you are generating the public key, private key, that's when you will share, and only after getting the values only you will calculate the shared secret key. Then we are mathematically secure. So based on the difficulty of solving the discrete logarithmic problem, we can say that is mathematically secure. Coming to disadvantages, first one we have is no authentication. That is, it is prone to man-in-middle attack without any, if additional measures are not taken here. Then we have computationally intensive. That is, when we are taking large prime numbers here, the computations are also more. Thereby, it can take a little more time to perform the operation. Then we have static key issue. That is, we are reusing the same keys can compromise to the security aspect. So this was about the advantages and disadvantages. Speaking about the key exchange protocols, so we have basically two types. One is the basic protocol and the other one is directory assisted protocol. So basic protocol will have users exchange public keys directly to each other and compute a shared secret key. That's what we have seen now. And speaking of the directory assisted protocol, a trusted directory will firstly store the public keys yi for all the users, and this will also this will allow any two users to compute a shared key dynamically. Thereby you are cutting down people who are trying to access the key. So if I am the third person and you both are trying to exchange the keys, I won't be entertained in such condition. So directory assisted protocols are a little better compared to the basic protocols. Next we'll look into the vulnerability, that is man in middle attack. Again, from exam perspective, this is very important because the Diffie-Hellman key exchange algorithm is very easy. Even just remembering the calculation part, you can write it very easily. explain it properly. Coming to this man in middle attack, a little you have to be careful here. So man in middle attack exploits the lack of authentication during the exchange of keys here. So there will be a third person who will intercept and alter the key exchange process. So a third person will be there between the sender and receiver. So this third person will take the signals from sender. He will deduce some content from it and give it to the receiver in his or her own desired format. Now that receiver will give the response. Again, he'll interpret it and give whatever he has to give or he has to show to the sender accordingly. So man in middle attack is a greater vulnerability. So we'll look into how it works and what is the like key exchange process. How does it happen here? So let's look into the figure. It'll be easy for us to understand. So firstly, here Alice is there. So Alice will send the public key. Alice will generate the like public key first. Alice will generate the private key XA, and then she'll generate the public key, that is YA is equal to alpha power XA mod Q. So once Alice has generated the public key and private key, and before that we have the common values Q and alpha, Q being the prime number, alpha being the primitive root of Q. So Alice knows, Bob also knows the prime number and alpha value. So even Dart will know the prime number and alpha value, okay, because they are shared in public domain. So here Alice will generate the public key and private key. Bob will also generate the public key and private key. So Bob will have its public key, private key pair. Alice will have its public key and private key pair. After that, Alice will send its public key. Alice will send its public key to Bob, right? So Alice will send YA here, and Dart will be there in the middle. Dart will intercept, and Dart will calculate his own public key and private key now. So Dart will generate his own public key and private key, and when here Alice has sent her public key, Dart received it. Dart will send his public key now. Okay, so Dart has got the public key of Alice, but then he'll send YD1 now. So he'll send YD1 to Bob. Bob will receive the YD1. So Bob will, after receiving the YD1, he'll send his public key now. So Bob will again send his public key. So Dart will again intercept, and he will send YD2 to Alice. So Alice was sending properly, Bob was sending properly. It is Dart who is playing along with the public keys here. So he got Alice public key here, but then he sent whatever he wanted to send, and Bob gave a response, and he got Bob's public key here, but then he's sending whatever he wants to send, that is YD2. And after sharing the public keys, next step is the key like secret key calculation, right? So here we'll start calculating. K2 is equal to, firstly we'll consider the receiver's public key, that is receiver here what we have got is YD2. So we'll write YD2 power our own private key, that is X power A mod Q. So that's how I have calculated the secret key for Alice. On the other hand, we have to calculate the secret key for Bob also. So K1, Bob will consider the public key of the sender, that is YD1. Here it is YD1 power his own public key, private key mod Q. So he'll get K1 here, and there is K2 here, and here also secret key is calculated. K1 is equal to YB, whatever is received, XD1 mod Q, and on this side we have K2. So YA XD2 mod Q. So here we can see that man in middle, so the middle person here, Dart, will share a key such that Alice and Dart will share a common key K2, and on the other side Bob and Dart will share a common key K1. So the messages between Alice and Bob are decrypted here, or they are altered or eavesdropped by Dart here always. So that's how this figure actually works. That's how man in middle actually works. So we have written down all the points here. So Alice and Bob will believe that they shared a secret key, but Dart controls both the secret keys, allowing them to decrypt and alter the communication process. So this is what I've written down here, how the steps actually work and all. So in order to prevent these man in middle attacks, we'll be making use of digital signatures. So digital signatures are those signatures. So we sign the public keys in order to authenticate who are the participants. Only those participants who have the digital signature should be entertained in while communicating with each other. And along with, now we have public key infrastructure. Public key infrastructure PKI will employ certificates to validate their identities. So thereby this will ensure that the integrity of the exchange public keys are maintained. So in this video we covered Diffie-Hellman key exchange algorithm, and then we spoke about man in middle attack. Next video we'll be speaking about the Elgamal crypto system. So If you have not subscribed to my channel, do subscribe. And if you have any doubts, do let me know in the comments. And stay tuned. Thank you.